Okay, this is the second theory video. This is chapter 2, which is curvilinear motion. Kinematics, not motion. Curvilinear kinematics. It's basically the same thing as chapter 1, which was rectilinear kinematics, except now the path is a curve. So chapter 1 was a straight line, and now it's a curve. That's all there is to it. Not much difference. So for these, there are the same quantities again: position, displacement, velocity, speed, and acceleration, right? Same things, and time is like the metric for all those. The independent variable for all those. What changes though is that we're going to be using a lot more position vectors for this section. So like position vector will have r is equal to xi hat. That's supposed to be with a hat. Y j hat and z k hat, right? Where x, y, z are just some random coordinates that are away from the origin. So we can have our origin anywhere. Like you can have this curve, right? You can put your origin here. What's this point? Well, this is just x, y, z, and then you make it into a vector by adding I hat, j hat, k hat. Nice and easy, nothing difficult about that. Keep in mind, of course, that when you do have position vectors, it can be a function, like so, which would then make it x of t, I hat, y of t, j hat, and z of t, k hat. I know there's like 3D mentioned and stuff, but most questions are going to be in 2D. Honestly, I don't even remember doing any 3D questions in class. We might have, but it's not in my memory. I can say that much. That was a lot more in statics. There's also the magnitude of r. So that's denoted like this. That's the square root of x squared plus y squared plus z squared, right? That's magnitude. This is like basic stuff from, you probably would have learned this in like statics or lineage if you did that before, or just whenever you learned vectors. You probably learned this in like high school. I feel like that's probably when you could have learned that. Yeah, so this position vector can be a function of time. Since it's position, there's nothing, you can't have it like as a function of anything else. It'll be a function of time. So that's what it looks like. And now we're going to have also displacement. Displacement. We're going to have, imagine we have our path like this, right? Let me just, no? Okay. I don't know why it didn't work. There, path. Okay, this is our path, s as a function of time. And we're going to have 2 points along this path, one right here and one right here. Right, so we'd have, let's say our origin is here as well, by the way. So we'll have one path, our two position vectors, like so. And to get this, for example, if we want to measure this, we can call this S average, or yeah, delta S average, because it's a change in position. So this is a displacement, right? It's just going to be the vector difference. So if this is path 2 and this is path 1, delta S average, now if you go back to typing, delta S average, and I'm going to be using this because I don't want to hold shift every time I want to do a subscript, is just going to be R2 minus R1, like so. So you should know how to do vector subtraction and addition and stuff. You should already know how to do that, but if you don't, it's just like component of vector 1, or component of vector 2 minus component of vector 1. So it'll be like x2 minus x1 I hat. y2 minus y1 j hat, and then same thing for z. All right. Anyways, moving on to velocity. All right. This is just delta s, delta r, whatever you want to call it. All right. This is just v. And this is average velocity, by the way. Average velocity is equal to delta s over delta t, right? That's just what this is. That's pretty easy. If you want to get the instantaneous velocity, right? That is calculus stuff. That is the limit, right? As t approaches 0. So the limit as t approaches 0 of delta s over delta t, right? Which is basically the same thing as dv dt. And to do this, you would just take, since this is a function of time for our delta s, it would have to be a function of time, or else, yeah, or else it would just be 0. That's when you would split your derivative. So you'd have like dx, dx dt, dy dt, and dz dt as your vector components, depending on your notation. I did say I was going to use prime notation last time. So it would be, you would have v is equal to, like this, x prime, that's x prime I hat, y prime j hat, z prime k hat. That's how that would work. All right. And then the magnitude, again, you would just use this concept right here, but with v instead, and then x prime, y prime, z prime instead of x, y, z. Right? Same formula, just use the components. Acceleration is exactly the same, actually. Oh yeah. Before we move on, I do need to point out here that, let me use a lighter color. The velocity vector is tangential to the path. That basically means it's going in the same direction as the path. If this is your path, this is your velocity. That's how that works, right? It follows the path, always. That's the velocity vector always follows the path, right? And then acceleration will be exactly the same thing, right? Just it'll be this but double prime. So let me just like copy this. Acceleration, right? It's this formula, but we just add on another prime to everything, right? Just like that. So that's acceleration in this for curvilinear kinematics, right? Again, the magnitude is the exact same thing. These are just, this isn't anything new, by the way. This is just chapter 1, but like everything's a vector now. So really easy. Really, really easy. Okay? That's the first part of chapter 2, right? This is the second part of chapter 2. Particle motion. Projectile motion. Well, I can't. Okay. Projectile motion. Good reading from me, I know. When you're doing projectile motion, it's really easy. Let's say you have this, right? Let's say you have a cannon, and the cannon shoots a ball. This is the path of the ball. Ooh. This is the path of the ball, right? How does this work? Well, it has a horizontal component and a vertical component. I drew the wrong ones when I said the words. but you get what I mean. It has a vertical component and a horizontal component. That's how that works. So in vertical projectile motion, right? I mean horizontal. Wow, I'm mixed up. In horizontal projectile motion, okay, this is moving only in x. There's nothing moving in y, right? And because of that, you will have no x acceleration. Imagine you've thrown a ball, right? Like this. Gravity is always going to be pushing down on it. But after you've thrown it, there's no forces acting on it left or right. There's no forces. So that means the acceleration, there is no acceleration right to left. Horizontally. There's no acceleration. That's how that works. So for our formulas, we'd have v sub x is equal to v naught x, right? And then we'd have, now this is the, if we go look here, this, oops, that's not the drawing button. It is these equations again, but I'm translating it to x coordinates only. You can see right here as well, there's particle curvilinear motion, x, y, z coordinates. These are just like the derivatives of what everything is. You should know this like already. I don't really think you need the formula sheet for this. You'd need it for this, honestly. Like you would not be able to ask me to memorize whatever the hell this is. Anyways, back to this. So this is our displacement. You have x naught plus v naught x, right? Because remember, all of these equations have acceleration, but they're just zeroed out. Zeroed out. So it's basically saying that your initial position plus your initial velocity makes your final position, right? Oh, I forgot the time. And then finally we have v squared. Vx squared is equal to v naught x squared, right? These equations are easy. Does not matter. Anyways, this equation right here is the big link in projectile motion, this middle one. In fact, it's so important, I'm going to write it out like so. Plus v naught t. Okay, ignore the fact there's no x's. There's also the half at squared, but we'll ignore that for now. Why this is important is because of this. T, time, right? You will be getting time in these equations. Basically, it links it because the time for, if this is your path, the time to get from here to here is the same up or down. Like you go up and then you come back down is the same as when you go right. It takes the exact same amount of time to reach that final position, right? Remember, so you're always looking for time, right? Anyways, these formulas are all pretty obvious. You only need to really know this one. V is equal to d over t. That is your main formula in horizontal motion. Anyways, for vertical motion, it's going to be same formulas, but it's going to have acceleration. So these are your formulas, vertical, right? And we're assuming constant acceleration, by the way. That's why these work. Yeah. So you'll be using these formulas, nice and easy for projectile motion. Nothing really difficult about them. See vid 1 for equation explanations. Anyways, moving on. If you have, or not moving on, that's it. That's it for this chapter. Really short chapter. Again, this is like high school, especially projectile motion. I did this in high school. I'd expect most people would have done this in high school. So there's like nothing that new, honestly. V is equal to d over t, right? These equations for y, really easy. Nothing to worry about. Oh yeah, in y, I will mention this though. The acceleration of y is just equal to g. G is gravity, negative g. I mean, it could be positive if that's your time frame, but like time frame, your reference point says gravity is positive. I don't know why it would, because usually the ground is your reference frame for these, but whatever. That's all there is to it. It's really easy. You would replace these x's with y's and then just add on acceleration. Exact same formulas, right? Nothing changes. This is important though. Your final velocity, and when I say final velocity, I mean in the case of when you go straight up, right? Imagine there's no horizontal movement, only vertical. Your final velocity is always going to be 0 here. Always 0. 0 is equal to VF. Always 0. I went over that in the last video, the last theory video, as to why that's a thing. At least I think I did. It might have been the problems video. I'm a little disorganized. But keep that in mind, okay? So if you ever have a question that's like this, and it's like, find the thing here, and you're like, oh, I don't know my initial velocity in y. That's fine. You know your final velocity in y. So you look over here. You know final velocity. You know your acceleration, right, with respect to gravity. And maybe you know your distances, for example. You know S0 is 0 as well in this case because you're shooting from the ground. You know S0 is 0 in this case. You have S, whatever, they could tell you. But basically, keep in mind that if you're studying straight up like this, your final velocity will be 0. That is very important to keep in mind. Okay? This does not apply, by the way, to x. Your final velocity at x, if you're going straight this way, v, constant. This does not change. That's why you use the constant velocity formula, v equals d over t, meters per second, just in case you wanted the dimensions of that, right? So that's this chapter explained. Really easy stuff. The questions are also pretty straightforward. I wouldn't be worried about them personally. I think they're all really fine questions. I do like projectile. Okay, I'm rambling now. I do like projectile motion. Fun unit, fun chapter, whatever you want to call it. Thank you for watching. Bye.